All right. So today, just a few reminders. We'll continue with the example we were working on last week, and I'll continue to admit people here. In the example we were working on last week, and we'll develop today the sums of squares, and then we'll link that back to the regression line. I also, because last week in the middle of me screen sharing from my iPad, I had a problem. I went ahead and I posted something that usually I would just sort of do live from my iPad, but I posted it and we'll go through that today. So that's a little extra thing on there. Just a reminder, it's in the syllabus, but no, I don't have any office hours tomorrow. I will have office hours, obviously on Wednesday, but I don't have them on Mondays and none tomorrow. So with that in mind, before we dive in, one thing I'm seeing that I didn't see last year, a couple people have had problems just getting R to start. And that's because you have to have R loaded. You have to download R first. And then after that, you download RStudio. So it lays it out for you in that link. But I know some of the, I don't think anybody here has that problem, but some of the 410 have gotten confused. So just be aware of that. Although you should have done that, a couple of weeks ago. I think you have because you're graduate students. So you're prepared for that. All right, so before we dive in, and we'll start with that Excel worksheet and talk about sums of squares and decomposition. What questions do you have? What would you like to review?
I have a question about the R coding. Is that something that we're going to learn in lab, I guess like upcoming lab, or is that something that we kind of have to learn by ourselves?
Well, we can go through problem messages. What I posted this morning, I think it was, I posted, and what I thought, and this is what Katrina pointed out, an exact walkthrough of this assignment. It turns out that you have much less data than I showed in that example, but that assignment goes, that video goes through line exactly what you do line by line by line. So that video coupled with the other two about how to read data, I think you'll be fine. So I know what people have liked to do in the past is have the how to do assignment going and then just, pause it, fill it in, pause it, fill it in. So I won't be lecturing on it per se because that video does the lecture. Did that answer your question, Gilbert? Bill? Okay.
Yeah, it does. Thank you.
Usually, because we were together all last semester, I don't like to have an exact do this, do this, do this assignment. But for R, for the first time, I think that's reasonable.
Dr. Oman, I have one question.
Yeah.
So in terms of the corrected R, I'm not sure where does that come from because it's in the assignment.
Yeah.
And
don't worry about adjusted R. I have not given you the formula for that. Don't worry about that. I'll show you actually where it is on the printout, but yes, don't worry about that. What else? All right, then let's get in. Let's start. And I should start. I am recording. This is good. All right, let's look where we left it. All right, here we all were. And we were predicting off from positive emotions. We talked about this. We didn't have time to go through this, but there are the equations and you can calculate that yourself. What I added, and I'll show you how to do this in SPSS, I saved the predicted scores. And typically when you're doing data analysis, you may or may not need to save the predicted scores. But in this case, because we're going to do the sums of squares, we do want to save. So let's just chat. Let me make these formulas a little bigger if I can. And we might not go through these in order. You move your charming face a little bit. Let's start over here, this mushy one. So just as in ANOVA, we had the sum of squares total. And if you think back to one-way ANOVA, we partitioned it into the sum of squares between groups, the explainable sum of squares, and the sum of squares within groups. That same logic holds true here. In that we're going to partition the sum of squares total into the sum of square deviations due to regression, so the explainable, and the sum of squares residual or error. So first, let's talk about just calculating the sum of squares total, the total deviation. And this should look really similar. I even put grand mean there, although I don't really have a concept of grand mean per se in regression. I put it there so you can link it maybe. So we've got y sub I, that means any person's score, minus the mean. We square it, and then we add it up. So we're going to get the sum of square deviations of each person's score around the grand mean. So our sum of squares total. And that should, I think that is quite familiar to you. And then let me shrink this puppy back down. And the way we did that was, I have to keep moving them around here. So we have a person score. So we have the 6.5 minus the mean. Mean was 5.01. And we squared it. So we had, we would have equals 6.5 minus the mean. And we want to square that difference. My running is super slow there. And we always want to subtract the mean. So remember, we use the $ freezes the column and freezes the row. End up with these square deviations. We added them up, the sum, and we ended up with our total sum of squares. Total was 15.8094. And we can put that, here's our source table. We can put that right here. So probably I could only see a few of you. So, and I've got you mushed along the bottom of my screen. So if you've got questions, probably I've actually have you covering up the chat. So holler out. Okay, so this is our sum of squares total. And then we're going to partition the sum of squares total in the explainable part. So that's the sum of squares due to regression. If we were thinking about this in ANOVA, it'd be the sum of squares between groups. So we can do that. And here we've got the sum of squares due to regression. And it's the predicted score. And we're going to map this on. After we do this right here, we're going to map this back onto the regression line on that with that other handout that sounds so retro. The other piece I have for the example. So the y predicted minus the grand mean. So remember we have the grand mean coming on here, and we're seeing how much better do we do by having a predicted score. So this is, this then is, here's the predicted score minus the grand mean squared equals this 195.75. And we square it, and lo and behold, we end up with 9.9506. So I can put this in here. And finally, this is the residual, the unexplainable. This is how far each person their score is away from the score we predicted that they would have. So this is how, really you can think of this as how wrong is our regression line. Remember, if our regression was perfect, then everybody's score would be right on the regression line. So to the extent that the regression line is not great, is the extent to which the scores are, way far away. So think about when we're guessing correlations, think about those really tight correlations, the 0.9s, all the scores were like just about on the line. And then think about the 0.2s, it was kind of a blob, they were way out there. So same thing. So we're going to say person score, here we've got awe, minus their predicted score. So we did pretty darn well with this first person, right? Their actual score was 6.5. We predicted they'd have 6.4. We were geniuses. So we have that difference squared at 0.007. So we were excellent. But take a look at this person here. Their actual score was 7. Lots of awe. We actually predicted it would be much lower, 6.29. So we were off. And you can see that that difference is larger. So we do this, you're good at Excel, and we end up with the 5.8588. And so stopping there, what questions do you have? Let me move up the little bar with your little charming faces.
Dr. Rahman?
Okay.
So when we say the regression line is not significant in predicting the dependent variable, so at that point, how can we measure that? Isn't that the SS regression is not significant?
It would be, a fantastic question. And actually a much more complicated question than you would think. We're going to test it. We're going to calculate an F ratio. And that F ratio, if it's significant, we'll say we have significant prediction. If it's not significant, then we don't. Now, the weird thing is, the strange thing is we test, well, I'm going to wait on that. I'm going to leave the question right there. Is we're going to use this, we're calculating F, and then I'll tell you exactly what that's testing. And then we'll talk about the weirdness in a bivariate regression. Did that answer your question, Jeff? All right. So in degrees of freedom, we have one for regression. We have 1 degree of freedom for each predictor. So how many degrees of freedom do we have here?
$19.
How many? I'm glad you're talking. That's first the most important thing. How many predictors do we have? 1. Yes, exactly. I'm good with Pictionary. I'm good with charades as well. You don't actually have to speak. We have 1. So we have one predictor. So we have 1 degree of freedom. We have 20 people total. And you know how the total degrees of freedom is usually n minus 1. So we have n minus 1. And here we've got n, the formula for this, for the residual, I'm just gonna write out the formula that we'll put it in, is n minus k, I'm gonna define this in a minute, minus 1. N is the total sample size. K are the number of predictors. And then 1, because we're estimating the grand mean. So in this case, we have 20 minus k, which is 1, minus 1 equals 18. And of course, happily it sums to 19. So then the same way of calculating the mean square as before. Degrees of freedom, it's not a surprise. 8 divided by 18. Okay, I don't really like to look at all these millions of decimal places. Let me see if I can move. Let me see if I can move you down here. And remember, it keeps all those decimal places. We just don't have to look at them. And then our F ratio then is our mean square divided by our F ratio. So 30.57. And our degrees of freedom are 1 and 18. So you can look at a calculator, or I think there are tables here. does it does not include it. That's okay. I'll just tell you it's significant. So to answer Jeff's immediate question, yes, we can significantly predict awe from positive emotion. But a couple things. Notice there was nothing about a direction, nothing at all. So I want to go through the different kinds of hypotheses we have. This F ratio tests multiple R. Let me just put it down here. Our multiple R, how do I want to do this? Principle is that multiple R, and APA format now says you can just have capital R equals 0. So, and sometimes that trips people up, sometimes not. It depends on the group. Capital R is different than lowercase r. This lowercase r is bivariate. There's just two variables. Multiple R is more than two variables. I'll put a little extra except in bivariate regression. So here we're saying this F ratio here is saying, is this multiple R 0 or significantly different from 0? That's the null hypothesis. So our null hypothesis of multiple regression always is the multiple R 0? And it's tested with this F ratio. Then what we're interested in, so we would write this so the APA format with R, we have not calculated that yet. And then we want to have R squared. I guess it gives you time to think, time to catch up. I've been thinking about that. We have F. Oops, sorry. We have, I'm going to fill in those values in a minute. We have F with 1 and 18 degrees of freedom equals 30.57, P less than 0.05. Now, what's going to be fantastic here is you'll see that we calculate multiple R a lot of different ways in regression. But first, let's just think about it as like we would have in sort of a direct ANOVA analogy. So we could, remember we have eta squared here often? Eta squared is just R squared. So I can put a column there if I want it. And how did we calculate eta squared before? From the textbook, how do we calculate R squared? I could look up, find where it is in the textbook.
I mean, Dr. O'Malley, are we just supposed to square the R value?
Yeah, but how, well, you could, absolutely, you could just square the R, but, and glad, thanks for talking. But we don't have R. So how could we get it? So when the hint I gave you is R squared is identical to eta squared. They're the same thing. So many, many, many times last semester, you calculated eta squared. How'd you do it? Or let me find out where, see if I can pull out the old textbook that you're reading.
Dr. Roma, I think we can just use regression divided by total
Do. Hey, Jeff, I
for
appreciate it.
sum
Absolutely.
of square.
Absolutely. Absolutely. We divide the sum of squares for regression by the sum of squares total. And then we can convert that to a percentage, of course. And we would say, what are the grandma terms for that? Don't make Jeff do all the work today. He's brilliant, but we don't want him to be overworked. Oh, I see some things in the chat. Hold on. Yes, yeah, Emma, you got it. Yeah, I'm not able to send this file, the link. I just before class, I downloaded it from Blackboard without a problem. What are the grandma terms for this? Something in the chat, maybe? Yeah, 63% of the, okay, yeah, I've got both of them. 62.94% of the variance. Okay, so this is regression. So we're predicting. So I'm glad, Ashley, Emma, thank you. But the right answer is between the both of you. 62.94% of the variance in awe is predicted by or explained by positive emotion. So now we can see more than shared variance because we're actually saying we want to predict awe from positive emotion. So we can really say how much variance in awe is predicted by positive emotion. And we want to go to 2 decimal places. So good, thanks. Now, so we can plug in here. Let's get back to this. We can say R squared equals 0.6294. And Jeff said this, we get to R by taking the square root. Equals, so we can sort of back into it. 7933. Let's put this together. So what we're doing here is we're testing, I lost, oh, it just got hidden once. There you go. We're testing this F ratio, the 30.57, is testing the null hypothesis that multiple R, this capital R, equals 0. So what we're asking with this analysis is this 0.7933 significantly different from 0? And our answer is yeah. And then just like always, we want to explain it. So we want to be able to say, well, how important is it? So the measure of importance, of course, is R squared. So 62.94% of the variance in awe is predicted by positive emotion. And then here's your full APA format statement. And what some people get tripped up on is the idea that multiple R is 1 dV and 1 or more independent variables. So 1 dV and 1 or more predictors. This is multiple R. This lowercase r here, like for instance here, the R, the bivariate R, that's just one predictor, or that's just 2 variables, 1x, 1y. So lowercase bivariate R is 2 variables. Multiple R could be 2 variables, but generally it's 1 outcome and 1 or more predictors. Questions? What questions do you have at this point? Please ask.
Hi, Dr. Orman. My internet just broke, so I kind of missed the whole grammar term. So do you mind repeat it?
Well, the grammar terms for what? We can have,
For the outcome,
for what?
for the outcome, I believe. I'm
For
not sure
multiple
what I
R,
missed.
we're testing, this is, multiple R is testing, it is our full regression line different from zero? So are we able to predict awe from positive emotion? So can we predict our DV from our predictors? And the good thing is that we're taping this. So you could, zip around in the tape and kind of mark where we talk, where you figure out where your internet zapped out and find us.
All right, thank you. I forgot it's being
I'm sure,
recorded.
no problem. I get the internet thing. I was having internet problems this weekend and kind of in a panic that something's going to happen today. Or hasn't. My internet is working just fine. What else? Okay. So now let's go ahead and generalize this. Ooh, I'm trying to be sort of I've got 14 things I want to do here. So let me just be systematic. So, yeah, so, yeah, 62.94% of the variance in awe is predicted by positive emotion. Let me get to next. We're going to jump around in this a little bit. And I'm going to see, I have you all in a, there we go. So this is, when you open this up, this is the top of it. But before we look at this, I want to go down to here. And we've got all this different color coding. So here is just a little scatter plot. The green is all data points. Positive emotion on the x-axis, awe on the y-axis. In this example, it's unfortunate, but our intercept is less than 0. So I just did a little crosshatch and mark 0 in there. And, we talked about regression, meaning can we predict better than if we just use the mean? And what we just did is we did the sum of squares decomposition for regression. And I want to show it to you here on this diagram. So first thing, we've got the mean is right here, the flat line. And then here's y predicted. This is the regression line. Y predicted the intercept plus beta 1 x1. So we've got the intercept and then, the tilt of the line is the slope. And now let's look at how we map on this 3 sums of squares. Sum of squares total, sum of squares residual, sum of squares regression, how that's mapped onto this regression line. I want you to see that link. So if we just take this score here, whoever we come up with your own name for the person. This person's score from here down to the mean, well, that's their total variability. This is how far this person is from the mean of all the scores. So this is this area C. And then we can divide area C, just as we've been talking about, just as we talked about, and then we showed in the source table. We can divide it into the residual, how far a person is from their predicted score, area B, and then to regression, the good stuff, the explainable variance, their predicted score from the mean. So what we want to see is, and you can see that area B plus area A equals area C. What we want to have happen, if our regression were fantastic, what would be, what would we want to see? Would we want to see B large, small, A large or small? What would we want to see here? C is going to be C, but what about the relative sizes of this area B and this area A?
So we want B to be small and A to be large.
Absolutely, absolutely. Thanks, Jim. Yeah, we would like B to be small. We would like the score. We would like this person's score to be on the regression line, and we want to have a fantastic job of prediction. So we want to have the prediction line to be way, way different. So yeah, perfect. Thank you. Okay, let's pause here and see what questions you have. This is perfectly crystal clear.
Dr.
If
Ullman,
it's not, yes.
when you said in reference to the areas, area A, B, and C, I think I heard you say that area B plus area A equals area C. Okay, just wanted to clarify. Thank you.
Perfect, perfect, absolutely. Yeah, clarifying questions are great. Questions where I understood until you said this and now I'm lost, those are good. You can't go wrong asking a question. So what we've seen here is in Excel, we did it with formulas and it was precise. Then here is a picture where you can see sort of relatively what happened. And then we would take, like for instance here, this is our residual. We would take everybody's distance squared, add it up, and that's how we would have the sum of squares residual. So think back to the scatter plots. We're doing guessing the correlations. Those residuals, we're saying imagine a line going through them. Those residuals would be really small if that correlation was high, if it was about 0.9. And you can see how the correlation, we didn't have time to go through it last week, but you know, the textbook's great. But you can see that the role the correlation plays in the slope coefficient. You know, that was clear when you went ahead and calculated those slopes. All right, we may use this a little bit more, but I just wanted to look at this very top part here. We're gonna look at the residuals a little bit later. So the regression line, we have this y predicted equals beta O plus beta 1x. So the intercept is some sort of, a spot where you anchor the regression line. It's the point if this example happens to be compassion, but if compassion were 0, what would awe be? But it fixes the regression line to the y-axis. And then beta 1 is the slope. So the combination of this makes the regression line. Notice there's no residual, there's no plus e here, because this is just the formula for the regression line. But look up here. Here, this is the regression equation. This is the full regression equation. And this equation is what really sort of we're partitioning. And you can see here, we have the intercept, which just is a scaling device or an anchor, plus the slope, some weight of how much of x, predicts y. This is explainable variance, this beta 1 x1. And then E, the residual, it's the unexplainable variance. Let me see, question? X1 is any score. That's a fantastic question. So beta 0 is the intercept. Beta 1 is the slope. And X1 is any plausible value from your data set. So imagine the range of scores goes from 1 to 10. You could plug in any value if you wanted to come up with any value at all. So when we were using the Excel spreadsheet, if we were to do this, we could calculate the regression line for all of the schools, or the regression equation for all of the schools. And then E is the residuals, it's the leftover. Questions?
Dr. Roma, just to clarify, I read this part from the textbook as well, so I'm a little bit confused about the y. But so this this y value is the exact value of the dependent variable, not the predicted one. That's why we have a residual in the end.
Yes, yes. So if we want to get someone's exact score, we would have to know, how much was explainable and then how much of it was residual. Yeah, exactly. So I don't want to go too fast here, so I'm worried that there aren't more questions. Okay.
Dr. Ullman,
Yeah.
so are you saying that the regression line is the predicted scores and then you use the regression equation to get the actual scores?
Yeah, and so let me show that again. Thank you for asking. Yeah, so typically we're interested in the predicted scores. So if we want to, and people use this, so they use it to predict who's going to be successful. The IRS uses a version of this to say who's going to be audited. Whatever you can imagine predicting, you sometimes might want to have to know what you would think their predicted score was. In which case all you would need would be the intercept and the slope. And then you say, well, if somebody has somebody has a positive emotion of 4, what would I predict their R score? That's different than this formula. This is a theoretical formula. You're not going to use that any purposeful way in an application. This is saying I could take someone's score, Sally's score, and I could have some scaling thing, but I could divide her score into the part that was explainable and the part that was not explainable. So I could for every single score in the data set, I could partition it into the part that's explainable by the predictor variable and the part that's not explainable. Ryan, did that answer your question?
Yeah, so basically the equation is just us having all the information and partitioning the variance.
Yes.
Okay.
Yes. And Alex, did that loop around help? Sorry, Jeff, did that loop around help?
Yeah.
Okay. So let's look at some printout with this example we have. I'm using the same class example. Okay. So here we've got it. And so it's comforting to see we have the same means, same mean, same standard deviations as we did before. It's really handy to have the SPSS output. I probably would do it first. I think many of you did do it first. And then you have your answer sheet. And from there, you can go ahead and do R, do your Excel, and you have something to see if you're right or not. And hopefully, particularly in Excel, if you're going to the cells and pointing and you're not trying to type things in, it should match exactly. So let's go down here. Let's skip some things. I'm trying a different way to sort of avoid some of the bivariate R confusion. We'll go down here. It's not ANOVA, it's just a source table. And you can compare Our sum of squares regression, same thing, 9.51, 1 degree of freedom, RF ratio 30.57. All of this matches exactly.
Dr. Ullman,
Yes.
I have a really weird question.
Okay. I'm eager to hear it.
Like where you're highlighting right now, it says dependent variable is the y variable ah.
Yes.
I thought the dv was, no, I have it written down as, sorry, I'm confusing myself. Ignore me. I have that written down. I just thought it said something else.
I can't tell you, and it's fantastic you asked. Seriously, fantastic you asked. I can't tell you how many times I have asked that exact kind of question, like, wait, or even if I'm talking to myself, wait, it's like this, no, oh no, yeah. No, that's what you illustrated with learning. That's a good thing. So yeah, the DV is off and the predictor is positive emotion. And notice that this is broken into two tables. We have the model summary and the source table. This F ratio, this 30.571 is testing, this is multiple R right here, is testing this 0.793 and saying, is it significantly different from 0? And the R squared, it goes to 3 decimal places. So 62.9% of the variance in awe is explained by positive emotion. So this F ratio is testing that. Now let's talk about, I didn't give you the formula for adjusted R. It's simple enough. I'll get it to you. But let's just talk about what adjusted R is, R squared. Think about how we calculated R squared. We took the square root of, well, we got it from the sum of squares. We divided the sum of squares regression by the sum of squares total. And so that's how we got R squared. And multiple R, we took the square root of R squared to get multiple R. So, and one important point is that multiple R goes from 0 to 1. Side note, or just awareness note, remember bivariate R can go from -1 to +1. That's a difference. Multiple R starts at 0 and goes to 1. So because of that, any chance errors, chance fluctuations only serve to make multiple R larger, and then so multiple R squared larger. So in order to, so it gets biased potentially. So in order to control for that kind of one-way bias, you know, that it's just going to inflate multiple R, it's going to inflate R squared, there's adjusted R squared, which adjusts for your sample size. People tend not to report it, but I think it's wise to pay attention to. If you've got a huge sample size, they're about the same. Smaller sample size will be quite a difference.
Dr. Ullman, can you repeat that? I lost you after you explained that multiple R is from 0 to 1, bivariate R is from -1 to 1, and why and what that all means.
Okay, perfect, thank you. So one thing is just the difference between multiple R and bivariate R. So for us right here, multiple R could be 0, meaning that you couldn't predict that you've got that flat line, or it can be greater than 0. It can never be negative. That means that any sort of little errors, fluctuations are going to just make it bigger. So if we have a bivariate R, it could be, and we have the same chance things going on. Probably some of them make it larger, some of it make it smaller. Not the case with multiple R. Any chance fluctuations are going to make multiple R and multiple R squared larger.
Okay, thank you.
Yeah, that's why we need adjusted R squared. Did that help?
Yes, thank you.
Dr. Ullman, do I have a formula for adjusting the R?
I do. I don't have it with me right here, but, and I'm not sure, let me check. I'm not sure the book. Let's just hold on 1 second. let's see. I'm looking. If you've got your book handy, take a look. They may not have the formula here. I'm not sure. I just want to check. I'm not seeing it here. I don't have it right on the top of my head. It's a simple formula, but I always like to make sure I have it right. Okay, now let's talk more about this multiple R hypothesis here. Multiple R is saying, can I predict the dependent variable from the set of predictors, from one or more predictors? So all it's saying, when you find that your R is significantly different from zero, it's saying, sure, you can predict. What it doesn't do is it doesn't say how you can predict. Or when we get to more than one independent variable, it doesn't say which independent variables you can predict. For that, we need to have the coefficients. So multiple R just says, sure, the regression line is, this would be the mapping kind of way, the regression line is significantly different from zero, but it says nothing more. It tells you how much variance in the predictor you can explain with the IBs. To know specifics, we go down to here to the coefficients. Here's the constant, the intercept. It's not significant. We typically don't pay a lot of attention to it. Here is our predictor. So we say for every one, we go, okay, great, I can predict. For every 1 unit increase in positive emotion, I predict that awe will increase 1.259 points. And my evidence is T with 18 degrees of freedom equals 5.29, P less than 0.05. And we got this T by dividing the 1.259 by the standard error by the 0.228. That'd be roughly 0.529. So this is sort of where SPSS sort of does you wrong. The slopes are lowercase b, they're not uppercase. Standardized coefficient is, say we wanted to compare, well, we'll talk about this later, but let me just kind of give you an overview a little bit here. We have more than one predictor in the model. We will say, well, what's the most important? This is like a standardized score. So you would interpret this as for every one standard deviation increase, how much does awe increase? So we say for every one standard deviation increase in emotion, we predict awe to increase 0.793. You'd have to look up and see what our standard deviation was. So for every 0.574 units of positive emotion, we would predict awe would increase 0.79. And then finally, confidence intervals, important. This is the confidence interval for this slope. So the 95% confidence interval for this slope of 1.259, it ranges from 0.780 through 1.737. So if you didn't have this significance, how would you know that slope was significant?
Because it doesn't include zero.
Yeah, absolutely. Thank you, Alex. Yeah, it doesn't include zero. Because remember, if we have a slope of zero, it's flat. So we've got a flat line. So if it doesn't include zero, we know probably with plot 95% that zero is not there. So we've got a slope. Questions? I see one in the chat, maybe. Yeah, for the end state, sure. Hold on, wait, which one? For the unstandardized coefficient, sure. You'd say for every 1 unit increase in the motion, we predict that awe would increase 1.259 points. And then you've got T with 18 degrees of freedom equals 5.529, P less than 0.05. What else? I think when you look at this printout carefully, you'll see there's a lot of duplication. And that's because it's a bivariate regression. And I'm going to, usually I talk about it more because I think it's really, really kind of neat, actually. But I also think maybe it's a little confusing when you're learning it. So I'm going to leave the discussion of everything that's the same in this outgroup for later. So before we go on to something new, what questions do you have? How are you feeling about the material? Excellent, you say. Good. Okay, I'm going to assume you're feeling pretty good. Okay. Then let's talk about some residuals. So your residuals are really hard to look at because you don't have many of them. So let's talk about them here, but then I want to show you a different example. Let me see this. Raylene, no. So for the standardized coefficient, what you've interpreted for every 1 unit, that's for the unstandardized. So for the standardized coefficient, you'd say for every 1 standard deviation unit, I think that's about what, 0.5749. We would predict all would increase 0.793 points. Did that answer your question?
Yes, thank you.
Okay. And always, you know, if it doesn't, it doesn't. First, let's look at your residuals, and then let's go look at some that are easier. Well, actually, let's look at some that are easier to read first, and then come back. Otherwise, I want to show you a couple things here. Linear. Doing, do you see the pop-out window? No? Okay. Thank you. Let me do this again. You see a pop-out window now? Really? Okay. Then
Dr. Ullman, by
yeah.
pop-out window, do you just mean where you're building the
Yes.
Yeah, we can see you building like
Okay,
where you
good.
put in awe into dependent and post-motor.
Okay, good. That's on the pop. I mean, I know how to share screens, believe it or not, even though sometimes it doesn't appear to be. But it's when the program pops up with another screen. You know, there's one of these drop-down things that sometimes it does, sometimes it doesn't. And we talked about this. We want descriptives. We always want confidence intervals. Let's get case-wise diagnostics, Durbin-Watson. The text talks about Durbin-Watson. I'm not going to because the text does a good job. And then for reasons we'll talk about, we want to look at outliers that are out of 3.3 standard deviations, because 3.3 corresponds to a P of less than 0.001. So if we want to say that something is an outlier or something is skewed, it's got to be really an outlier or really skewed. And we use a criteria, a p-value criteria of 0.001. And I just want to show you here, save. When I save the predictive scores, I just click that box and it shows up as a column in your data set. We could also look at these distances, Mahalanobis, Cook, and leverages, which are nicely discussed in the text, and you should definitely review those. We don't need to see.
Dr. Oman?
Yes.
So to get the YI, we just go to save and save the predicted values unstandardized? Okay, thank you.
No, that's the Y predicted. The YI is just your raw data.
Oh, sorry, I misunderstood that.
No worry. Oh, I'm glad you asked. I'm really glad you asked. Yeah, the Y lowercase I just means for every single data point in the
Yeah,
data set.
I meant the Y with like the
Little thingy on it,
superscript.
yeah,
Yeah.
the little T thing on the side. Yeah, that's Y predicted. Yeah.
Okay, thank you.
You're welcome. I'm glad. It's nice to hear questions. You know, it's weird. Well, you tend to be kind of a quiet class, but at least I can see you in person. And I see some of you, which is fantastic. But it's harder when we're online. Okay, so do you see printout? Okay, you share. Thank you. Now you see printout. I've jumped up the sample size. Now we have 1,686. And we see that still we can predict. And notice that when I vastly increase the sample size, notice the R square is not different at all. There is no bias. At a certain point, statistically, there's no bias. Durbin-Watson, refer to that section of the text that talks about this type of correlated error. Here's our slope, still significant. We're going to come back to these diagnostics in a second, but first, actually, let me go here. These are the residuals. I'd be the first one to say that SPSS doesn't do a very good job of graphing for us. But these residuals aren't particularly normal, except they look like they are. But I typically don't use that. But here's the scatter plot. And remember from your reading, so this is something you only had in the reading so far, we would like our residuals to be small, symmetric, and centered around zero. Small, symmetric, and centered around zero. So I think the textbook and I both kind of like to plot the residuals on the y-axis, the predicted values on the x. And you could sort of draw a line through zero, because we want these to be small, symmetric, and centered around zero. So what do you think about these residuals? And remember, these are z-scores. So the residuals range from a little over -4 up to, I think, about 3 or so. So in the text, you were talking about the section of the text. Like figure 3.7 or 3.9 or 3.9b, any of those are sort of similar. Certainly, you get a little gist of figure 3.5, but the cooks, we're not looking at cooks right now, but you can certainly get the idea from 3.7 in your reading. Let me ask another way. So when you did the reading, that part must have confused you because you're a little shy about talking. What part was confusing in that section? Or what part are you not able to take from the reading and to link to here? And I'm gonna let you go back and read that part. So I'm gonna let you read that part and also relate it to this and relate it to that big hint I gave you about these being small, symmetric, and centered around 0. And then from that basis, so I want you to have that core reading first, or have the core reading go, I didn't understand this part. I'm good with that. That's perfectly fine. That, and then from there, then we'll build on it with conversation and talk about how we interpret this and what you think, if these residuals look good or not. And remember, the reason why this is an assumption. So assumptions are generally evaluated on residuals, and we would like the residuals to be normally distributed. And we primarily, we use this plot here. I'm going to give you some hints here. Use this plot here. And then we also, I didn't give you Cook's distance, but I could. Actually, let's do Cook's distance because you've been reading about it. So this will be obviously on the video for you can kind of, well, I won't have it posted. So let's just save Cook. The book talks about Cooks and leverage. Cook's distance, and we'll talk about those anyway, probably on Wednesday. I like Mahalonova's distance as well. So let's just do all of those. So now we've got the same scatter plot, which you're going to look at. And then here are our case-wise diagnostics. So I tend to like the standardized residuals. I think are helpful to look at. The standardized residuals are what's plotted. And then here's Cook's distance, which is also discussed in the text. And leverage, they center. And Mahalo. Do you not see it? Do you need me to?
No, I don't.
Okay, thanks. Hold on 1 second. I was worried just as soon as that came up. Uh-oh. So here's the standardized residual here. These are, I'm giving you some things for you that we'll begin with on Wednesday. And here are standardized residuals are very helpful. That's what's in that plot. And then the book talks quite a bit about Cook's distance and has a great plot on leverage. And we were seeing a little on the leverage issues in the guess of correlation. So these two will link exactly onto your reading. So we'll definitely talk about those. So then on Wednesday, we're going to start with this because I'm just sensing that you're not comfortable enough with your reading that you're ready to talk and you're not comfortable with questions. So reread that section and we'll do this part. Additionally, for Wednesday, it'll be absolutely critical that you have done the first reading of chapter 4. So I'll give you a sort of the primer of where we're going. So what we're doing, we're going to do this cleanup on residuals on Wednesday after when you're able to talk about it. And then what we really need to dive into is doing ANOVA through regression. And that's chapter 4. And so the way I would approach this is I like, they have the basic organizer at the beginning. Certainly reading that carefully, that gray part, minimally looking at the diagrams, the pictures, or reading the headings and looking at that. But the more you can go into it, the better. The reason I'm talking about this so much is that we're going to go back. Remember we did orthogonal polynomials? We're going to do those again. And we're also going to do dummy coding. So if you didn't have 641, don't panic. It's all here. It's fine. But do take some time and work on that so that it's not stressful. What we won't be working on, the part of the chapter you don't worry about, is we aren't going to do this year. We're not going to do unweighted effects coding. Page 86, 87, and we're not going to do weighted effects coding on 89. So what we're going to focus on are two things. We're going to focus on dummy coding, and then we'll also go back into contrast coding and see how that works. And then if you were in 641, we can chat in labs and stuff and figure out the contrast coding. So let me recap what we've done then. We developed the sum of squares. We linked how the sum of squares links onto the graphs. And then from there, we looked at printout and we looked at this first set of hypotheses. So we're going to end up with a whole list of hypotheses in regression. We've got multiple R. Is multiple R significantly different from 0, knowing it ranges from 0 to 1. A second important hypothesis is slope equal to 0. The unstandardized slope equal to 0. Those two. Along with those, we're also exceedingly interested in multiple R squared. Very interested in what percent of variance in the DEV is explained by the predictors. And then we looked at the standardized slope as well. And then we didn't get to the R because my sense was, I could be wrong, but my sense was you weren't quite prepared, or you weren't prepared enough and brave enough to talk. So that's okay. That can happen on Wednesday. And Wednesday, though, we do need to make sure we jump ahead to ANOVA. Sound good? Are there questions? Okay, then why don't we go ahead and stop all of 5 minutes early, or actually, yeah, 5 minutes early. And then we'll go ahead and start lab 1, lab 2. And in the labs today, I have no extra lecture. It'll just be time for you to work and then go through that new, the new video, which I'm gonna have to check. I thought I was giving you the same exact assignment. It looks like I gave you a much easier assignment than I did last year. So it'll still be the logic. Everything is the same. It's just the data set's a little bit small. Is that what you saw when you went through it, Katrina?
What I saw was that there seemed to be a lot more dividers in the data as well as being a lot longer.
Right.
Because you were able to sort by like age and gender, and all we have are 2 columns of data. We can't sort by that.
Right. So yeah, there's a lot more data there. And this time you just have 2 variables. So
yeah. And you also had like 78 points and we only have 18.
Right. So I said it'll all be the same except your N is smaller, so a little more simple. Okay, well then I'll see you in a little bit. See you later.